Welcome back, everyone, and we're back to do more particle system updates to our emitter. The first two videos we'd talk about the actual particles. We're just points on the screen that we're controlling using a feature in WebGL 2.0 called transform feedback. In case you're new to this series, a transform feedback is a way that allows us to modify and keep state of data on the GPU. So instead of having all the data being computed on the CPU end, all the data is pushed to the GPU, and then our fragment shader, our vertex shader, actually does all the computing for us, and then saves the state back into the GPU buffer. This allows for a performance increase of like I say, a big performance increase. When you start dealing with thousands, if not hundreds of thousands of particles on the screen, having everything done on the GPU end completely done on it actually makes everything faster and easier to control. If you had to do everything on a CPU end and then push it to the GPU at every single frame, your frame count will drop dramatically. So it's a big performance boost by performing all this calculations on the GPU and keeping it on the GPU. All we do is do initial push of data, and everything else the GPU kind of takes care of for ourselves. The only thing we push to the GPU at every frame is basically time, because time allows our animations to move forward. So in the last two videos we did points. Now we're going to deal with meshes, and to create meshes with transform feedback and instancing, we have to do it differently. Before, we were able to do two VAOs that we swap back and forth. When we're dealing with mesh data, we can't do that, because when we're dealing with points and we're just dealing with one point, we can perform our calculations and our rendering in one draw call. That's because we're just processing one vertex at a time, and each vertex is a particle. Now, when a particle is multiple vertices, we can't do that, because take the idea that, let's say if we have a quad, it has 4 points, but we need to make 2 triangles out of it, so we need to do 6 vertices, basically. So a quad is really 6 vertices, but we use indexes to duplicate our vertex data. So at the end of the day, the GPU sees 6 vertices. So if we're computing a single particle position, let's say we're moving it, our particle once every frame, but if we're rendering 6 vertices per particle and we're updating the position 6 times, our particle is going to move 6 times faster than it really should be. The animation will get janky, and things will just won't render correctly at all. I even tried it. It just doesn't work. It kind of just flops on itself. Like, try to make triangles move, and it just was really bad. So it just doesn't work that way. So the way to do mesh data as particles, you have to break the process into 2 steps. First, you compute everything with a transform feedback shader, and then you take that information and then you kind of incorporate it into your drawing shader, your rendering shader. So it's 2 shaders we need to create. One's for computing and one's for rendering. And one good example of mesh data as a particle system is like asteroid fields. You can have all the mesh instanced as many times as you need it, and each instance can have like certain bits of information. You can have a vector, so it knows which way to move. And you can also have rotation. You can make so while it's moving, it can be rotating on a certain axis. You can pass in like acceleration vector. We can pass in a rotation axis and rotation speed. So this way, we can have all that calculated on the GPU, and it can be changed by time. We can also pass in things like user interactions if we want to. We can pass in like the player's position, or we can pass in like a bounding box or a bounding sphere, and we can have all of that. We can just pass in just small bits of information about that to the GPU, and then it can then calculate all that on the GPU end with all the instances. Like basically every single particle can be calculated, and all the values so you can move things around, so things can respond. based on user input, but all calculations can be done on GPU end. So that's the only thing we would end up passing to the GPU at every frame if we're looking for interactions. But for the bare minimum, what we kind of need is maybe time. And even then, you can live without time as well, because you really don't need time. You can just have your particle move constantly. It's just nonstop. It has no life. The whole point of time is really for life, so we can reset our particle into a new position, and restart the whole process again. Excuse me. The other thing you can do is like blades of grass in this way in a big terrain, and that's what we're going to do in the next video. But for now, we're going to set up how do we accomplish doing all this with mesh data. So in this video, I'm going to do something different, because since this is a complicated process, this requires to do quite a bit of thinking, and we're going to build VEOs and buffers completely differently than how we've done in the last 50 plus videos. Before every VAO, we built a buffer specifically for that VAO, and that's it. This time around, we're actually going to build a bunch of buffers, and then we're going to have them shared between several VAOs and feedback objects. So here's the plan. It's a two-step process. So first, we need to set up our transfer and feedback. So we need to set up two sets of VAOs, one to handle read and write, and to alternate between them, between the two. So we set up a VAO as our read for our buffers, and we set up a feedback object to write to that buffer. So it's the same buffer, but they're going to be shared between a VAO and a feedback. And in case you don't remember, a feedback is a way to write into a buffer. So VAOs gives us access for reading the buffers. Feedbacks gives us access to write to buffers. So that's read and that's write. The second step of our plan is that we need to set up our rendering VAOs. So again, we're going to have two VAOs that we're going to alternate back and forth. This VAO is going to have mesh attribute buffers. We're going to have our vertices, we're going to have UVs, and we're going to have our index. This data will be this will be considered one particle. So we're going to have like 4 vertices, 4 UV coordinates, and 6 index values. All of that accounts to a single particle. In the last 2 videos, a single particle only had 1 vertice, and that was it. So like I said, this dealing with meshes is a more complicated animal. So that all this information accounts to a single particle. So in those VAOs, we're also going to share the buffers that we use for the feedback reading. So the VAOs that we created here that uses the buffers meant for reading, we're going to share those buffers also in our rendering buffers. So certain buffers are going to be shared between our transform read, our transform write, and our rendering. So it'll be the exact same buffer, but shared across 3 different objects on the GPU. And on top of that, these shareable buffers are going to be treated as our instance data. So if we have 100 offset items in our buffer, that means that's 100 instances. That's how many instances of our particle that we need. So that data that we're computing is our instance data. It's basically the state of every single particle. So that's probably the best way for me to explain it, is that this part, the first step, is to update all the information, all the state information of our particle. And the second step is to take that state information and render our particle based on that data. So, and here's what we need. We need 13 buffers. We need to do 13 buffers. We need a vertice buffer, which is we're going to use just for rendering. We're going to need a UV buffer, also for rendering, an index buffer just for rendering. Our offset buffer, we need to create 2 of them because we're going to alternate back and forth. We need it for our render instance, for our transform read, and for our transform writing. Because velocity, we're also going to create 2 buffers for velocity. One is for reading and one is for writing. age, also for reading, for writing. Life, we only need it for reading, only for transform reading, because that data doesn't need to be changed. If you want to make life, if you want the life of your particle to change at the end of its life, so this way, at the beginning it can live for 5 seconds, the next time around it can live up to 8 seconds, you can turn that into, then you just create, then you just apply it to the TF-right if you need to change it. And then we have age normalized, and this is different because we didn't use it in the last videos. Age normalized is a value between 0 and 1 that tells you exactly at which point the particle is within its lifetime. If it's 0, it's right at the beginning of its life, and if it's 1, it's the end of its life. That means the next frame it dies. It gets reset back to 0, and all the values that we write to gets reset. Velocity gets reset back to its initial state. Age gets reset back to 0. Offset gets reset back to origin. So this helps us, do that. And what we need this for is actually for our render instance, because we need to, when we're rendering, we want to know at what point in its lifetime this particle is, because we're going to do certain things like at the end of its, as it gets older, we want it to fade away. As it gets older, we want to make it go bigger, or we'll make it go smaller, things like that. So we need to know how old is it, basically. And in the end, we need to create 4 VAOs and 2 feedbacks. We're going to create 2 for reading, 2 feedbacks for writing, and 2 VAOs for rendering. And that is the plan. This is what we need to do to accomplish transformer feedback when instancing with a particle system that uses mesh data. That's a mouthful. All right, excuse me. I have to do that away from the mic. Sorry. So first thing we need to do is do one small change to shader.js. At the very top, we're going to do a small change to load shader. And we're going to add this line of code. What we're doing is being able to change or turn on sample alpha coverage feature in our material, because you need to do some blending, and this because we need the alpha of a color, but this blending does not work properly, and we need to use this one. Problem is this one also comes with some issues, so we're going to go look through. We're going to look how these 2 blendings work and some of the things I've tried to do. But you're going to see there's some pros and cons with different blending modes. So yeah, and it's not going to be perfect, but it gets us where we want to go. So we just need that small change to shader. Now, like I said, we need 2 shader programs to do the job. So the first, we're going to have one called Transform FB Part 1 and Part 2. So this one is basically our compute shader. This is where we're going to do all the mathematics. We're just going to do no rendering whatsoever. So this is basically our regular material or shader information, and we're passing in the array of all the variables that we need that's going to handle the output that's actually going to be read into. So just like in the previous videos, this is all our reading buffers, and this is our writing buffers. Now, this offset and this offset are the same buffers, but on 2 different VAOs. So this is probably VAO A, and this is from VAO B. And then, let's say in the first frame, we're going to read from A, we're going to write to B. The next frame, we're going to read from B, and we're going to write to A. And we're going to alternate back and forth for every frame. So that's how transform feedback works. That's why it's called a feedback. It's a feedback loop. It's back and forth. It makes a constant loop back and forth. And everything else is the same from our previous videos. I just changed certain things. Instead of calling position, I'm calling it offset, so we don't confuse position with our regular shaders. Velocity, age, time, all of it is the same. The only difference is age normalized. We just take the age that we calculated and divide it by life. That gives us a value between 0 and 1. And the one thing you'll notice is that our fragment shader, we need a fragment shader to create a program, but it doesn't do anything. It doesn't compute a color. It doesn't compute a fragment color. And you might also notice that our vertex shader doesn't return GL position either, because you got to remember, we're just computing things. We're not rendering. So the things that are missing is related to rendering. So this is what our even though this is just a regular shader, we can consider this a compute shader, because OpenGL has something called compute shaders that kind of works. The idea is that it does all the calculations on the GPU, and then you can get all that data back, because GPUs can do all these calculations in parallel really quickly, very well, better than the CPU can. So essentially that's what we're doing. Kind of this is a poor man's compute shader for WebGL. Now we're going to our render shader, and our render shader is like every other shader that we've had. Now the only difference is we're trying to turn on this other blending mode that we set up in our shader.js, and these two are our particle information. This one, and these two are our feedback information, and we're sharing it. So that compute shader calculates offset and age normal, and then we're able to incorporate it into our rendering, and these will be treated as indexed. So while we're rendering like a quad, let's say there's 6 vertices that we're going to render, it's always going to use the exact same offset. It's going to, and then when we render the next instance, it uses the next offset on the list. So it doesn't loop through all the offsets in the same way that these two do. These are instance attributes. So all the vertices share the exact same offset and the exact same age norm. So basically it's what binds the entire particle together. So this defines the entire particle, and this also is state information of that particle, but it's our instance information. And what we're doing is we're going to pass to our fragment shader our UV, so we can do some fun rendering with it, and we're going to pass in its age because we want to do some things related to age. We're going to calculate our vertex position. We're going to do some math to it later, but for now we're going to just use it. And all said and done, we need to move it because our compute shader moves things. So we're going to add our offset position to the current position of our vertex, because our vertex exists in local space, and we're kind of moving it into a different part of open space. And then model view, camera view, it all brings it into world space and so on and so forth. And now we're going to look at our fragment shader. It's pretty much a simple fragment shader, similar from the previous video. We have something. I'm going to show you how to use discard. You don't need it, but it's a cool little feature to help. It helps fix something, but also gives you there's a pros and cons. But it's a cool little thing to learn that you can use in your fragment shaders. And there we go. Those are our two shaders that we need. All right, now we're going to go into our actual code. So we're going to load in our 2 shaders, right? We got part 1 and part 2. And we create our emitter mesh, and we give it our 2 materials because of the 2 shaders. Because the shader thing I built, you just can't apply a shader. You have to apply a material to it. So so we got our render, and we got our it extends renderable. So our renderable has a material for rendering. So we're also going to do material feedback because we need access to the feedback shader. They're basically, I want to call it a compute shader because it's doing all our computing. Oh, excuse me. Oh my God. Sorry. So we're just getting that material from our resources, and we're setting it as a triangle, and we're turning off culling because we want to see the backside of our quad. We want to see both sides of our quads. VO count is how many vertices that are within one particle. Instant counts is how many particles we want to render. How many copies of these do we need to do? So it's this times that, technically. It's how many vertices we're going to render. Current index is, it just alternates between 0 and 1, so we know which buffer set we're currently using. Are we using A or are we using B for writing, reading, and rendering? So we're going to have build. Build builds up all our buffers and our VOs and feedbacks. So it's a lot. So I create a bunch of shortcuts because I want to make the or a bunch of aliases. I want to make the code a little bit smaller so it's easier to read on screen, so it doesn't like extend too far out. So in case that's why you see that, I'm just doing that to shorten out the code line, make the line shorter. So like, I want it to be more readable because we know what these are. We've seen these for the last 50 videos. So we're going to create our two sets. And so we're going to set up our read feedback, which is two VAOs, and we need our writes feedbacks, which are two feedbacks. So those are our read and write feedback objects on the GPU. Count is how many, particles we want to create. So we're going to start, like I said, in our plan, we need to create all our buffers. So, buffers, we need A and B, velocity A and B, age A and B, whatever, so on and so forth. And I explained all this when I was showing off the plan. So this is where we're actually creating all our buffers, and we're creating them as arrays. Like, remember, this we're doing all this right now. And the only buffers that we need to fill up with data initially is life and age. And so with life, everything's in milliseconds. So we're gonna have a random age between 1 second and 7 seconds, because we're going to random number between 0 and 6,000, and we're going to add it to a base value of 1 second. So like I said, every particle will have a life, a random life between 1 and 7 seconds. And then we're going to set up its initial age, and we want its initial age to be basically death. So so we're going to take its life value, we're going to subtract since start, and we're going to subtract 1, because if we do this, life will be at the very end. It will be like it's the end of its life. But we want to make sure that the first time we run our compute shader, or shader, it's not really a compute shader, but like I said, I want to call it a compute shader. The first time we call it, we want to be able to run this right here. Age is greater than life. So we can run this because this will set up our offset, our velocity, and our age normal for us. So this way we don't have to do it on the CPU end. If we can do everything, if we can do some of this stuff in the GPU end, why not? And we need this stuff anyway for when the life ends, we reset it. So if we're going to reset it, and might as well reuse it as our also initial state. So that's why I just say, okay, here's the life, and then minus 100 to make it older. So it's over. So age is over life. The value of age is greater than life. That means let's reset everything. So this way you can actually set whatever age you want, and this would automatically be a few milliseconds older. So in the previous videos, I've been hard coding the age value. Now I'm making it dynamic, so we can actually make this into a constant, or a variable, and change the overall length of life a particle can have. Okay, so that's all our buffers that we're setting up, just to handle our feedbacks. This is all our feedback stuff, and offset and age normal will be also shared with our render object. So now we're going to create our two sets of VEOs and feedbacks. So like I said, offset, velocity, and age normal is going to be created on the GPU end. So instead of passing in data like we're doing for age, we're just going to compute the size of the buffer. So let's say if we have 10. We want 10 instance. Each instance of the offset is 3 floats. It's a vec3, so it's 3 floats per instance, and each float has 4 bytes. So it's 10 times 3 times 4, and that's how many bytes of data the buffer needs to be to hold all the data we need for all the instances, for all the particle instances that we're going to create. We do the same thing for velocity And we do the same thing for age. As you see, I mark it as empty because these are empty buffers. We're not pushing data to the GPU. The only data we're pushing to the GPU is age and life. Age is decopy, dynamic copy, because we're going to change the age, because the age is going to be random or is going to be reset, because we need the starting point of every age. So that's going to always be reset at the end of every life. But life is not going to be dynamic, so it's static draw. That's why I could just call it sdraw. If you want to be dynamic, like I said, just make it a decopy, and then you would actually just add it to your feedback. So now once we're done creating the VEO for our reading, to read our feedback information, you make sure you clear it out, because if you bind the buffer, you'll end up screwing up your VEO. So once you're done setting up your VEO, make sure you unbind it to null, so this way you don't screw it up. Then we just basically create our feedback. And our feedback functions very similar to how VEOs work. It's the same idea. You just bind something while that thing is currently active. So we give it back our feedback ID that basically are like struct, and we say, okay, this feedback struct on the GPU, we want to set offset, velocity, age, and age norm as the variables for our compute shader. Basically, it's these positions. And the positions can be different. So our read positions in the shader, can be different from here. So if I were to, like, let's say, move this down here, offset now would be the value be 0, 1, 2, 3, and this one would be 0. So that would be 3 and that would be 0. Okay. And look at it, that offset is the same buffer that we're sharing for the VEO. So the buffers can be shared between all these different like struct objects. You know, VEO is kind of a struct object. Feedback's a struct object on the GPU essentially. If you want to see how it in theory how it looks like on like in memory. It's kind of like a big huge array, and you could just point to it. That's why these location values are kind of like the index of those arrays. So yeah, I guess essentially these are structs with arrays essentially on the GPU memory. So that's, you know, like I said, this is the same thing we've been in the last two videos, setting up our writing buffers or writing access to our buffers. Like I said, these buffers don't have read or write access. VAOs and these transform feedbacks is what gives us the read and write access to those buffers on the GPU. It gives us the way in to use them in our shaders. So now that we're done setting up our feedback, now we go to plan. The second part of our plan is to set up our rendering. So we're going to create render VAOs, and again, they're just regular VAOs. We save it, and we're going to create our particle information. So we got our index for our quads, and we're going to bind it, and we're going to push it to the GPU, and we're going to use that as our vertex count for our particle. So this particle will have this many vertices that needs to be rendered for one particle. The next thing we're going to do is set up our vertices. This is our quad. This is the information for our quad. We bind it and we push it to the GPU. Mind you, we don't have VEOs set up yet. We have them created, but we don't have them bound. So even though we're creating our buffers, they're not bound to the VEO yet. We're just creating buffers first. So we're just creating buffers first. And then we have a UV data, and this is for each vertex attribute. It's basically a vertex attribute. And now we're going to build our VEOs. Now we bind our VEO. We say, okay, this VEO is going to point to this index. We bind our vertex buffer. We tell it what location in the shader it's going to be. We're going to tell it how many components it is and what type it is, and we're going to enable it. And we kind of rinse and repeat for every piece. So these three buffers that we're binding to our VEO, these are all this consists of a single particle, just one particle of information. Now these two, these are our instance data. These buffers will determine how many times we're going to repeat these buffers. So we got the offset. So for every big chunk of this, we're going to have a position that we're going to move all that data to. And this whole, all that particle is also going to have normal. And it's the same thing as we bind it. We tell the VEO how to handle that buffer data, where it belongs in the shader, and we enable it. And we just do this extra thing. We tell it it's an instance. And we tell it the location of that variable in the shader. And we say we just want to use it once per particle. So it's going to go one element at a time. So it's going to only use one offset at a time for every single instance that we're rendering. Same thing for normal. So every instance, it's going to grab it's only going to do it once, but it's 3 components. So it's going to grab 3 floats for every time we render a quad. So those 3 floats will be shared for all the vertices that we're rendering. Same thing for age. Age is just a single float. It's just one component. So as we're rendering our instances, it's going to grab just one float at a time, and that one float is shared for all of these guys. And then at the end, we just do our cleanup, and that is how we set up our rendering VAOs that accesses our feedback information, and they're the ones that actually allows us to create instancing. Now we're at the final part. Now we need to set up how do we draw this. Like I said, it's a 2-step process. So first thing we need to do is turn on our compute shader. So we turn it on. We make it the active shader that's currently on. Because you gotta remember, OpenGL is a state machine. Everything is state, and we can only have one state at a time. So we can only have one shader active at one time. So we're gonna activate the compute shader. We're gonna pass it time, because we use it to help calculate how old the particle is. And we're going to calculate or figure out what is the shader that we want to write to. So the current ID that we're currently at, we're going to read from, and the next is what we're going to write to. So we're figuring out which VEO we're using for reading and which VEO we're using for writing. Even though I say VEO, this is an actual VEO, and write feedback is just a feedback object. But like I said, the feedback objects and VEOs function in a similar way. They perform the same type of function, but they do it for 2 different things. One's for reading, one's for writing. So we bind our read, then we bind our write, and we tell the GPU, do not run the fragment shader, because we don't have a fragment shader, because we just want to compute data. We're not rendering anything to the screen. So we have to disable rasterization, or actually enable. It's like a not equal type of thing. We run and enable a feature, but the feature that we're enabling disables fragment shaders. So basically, we're saying this whole line is saying we're going to disable the fragment shader. Do not run it. Only run the vertex shader. Then we begin our feedback, and we're treating our data as points. It's just one point at a time. That's it. Each point in all those buffer arrays is just a single state for each particle, and then we just draw, and that's how we get the draw events. That's how we get the shader start running, and we run it as a point, and we tell it how many are there, and there's 100 particles that we're trying to keep state of. So that's how many times we're running draw events, or how much data to render in our arrays. When it's all said and done, we turn off our transfer feedback. We turn fragment shaders back on, and we unbind our transform feedback. And then when we go to rendering, we go to our original material. We activate the shader. We bind the next shader, because right here we read from current index, and then we wrote to next ID. So now we're going to render from next ID. So like this is the first frame. We're reading from A, we're writing to B, and we're going to render B, because B initially has all the data initialized, where A is still empty. Next frame, A will be initialized, and we can render from A. So that's why we're going to render the next one first, then we render A. And then so once we set we set buffer, basically render buffer B for rendering, and then we just render at instance. We have the draw mode already, how many vertices are in our particle, and how many times you want to repeat that particle. So it's like, 6 times 100, and that means you're going to render 600 vertices. All said and done, we unbind it, and then we say our current is our next. So this way, the next time around, we read from B and we write to A, and then for every other frame, we swap back and forth. And that is our shader. So if I were to refresh, and this is a quads being rendered in a transformer with a transformer feedback. And it's the same thing that we had in the previous videos, except instead of having just little points that are moving, we have quads. These are actual quads. Now, I wanted to show you some issues with blending. If you pay attention to some of the particles, you'll see that the fading between the alpha state is not smooth. It's kind of jaggedy. It kind of just pops from fade to fade to fade. That's because of the blending mode we're currently using. The blending mode allows us to blend everything in the same draw call, but it doesn't blend alpha, like transitions of alpha smoothly. It just doesn't. I tried multiple ways to do it. Go to render. So let's say, if I turn off this blend state and then turn off the other blend mode, empty cache, because sometimes I need to do this, else the shaders don't reload. Now if you kind of just focus on one, you see that it kind of fades more smoothly. But there's a problem. It doesn't blend very well. Certain vertices don't blend well. You still see the rest of the quad. As you can see, these are actual quads now that we're rendering. So even though the alpha animation or the alpha transition is a lot smoother, the blending doesn't work very well in single draw call. Now, one thing you can try to fix it with is by discarding colors. So right here, I have, if the alpha is less than 0.1, discard. Basically, it's a return null. You're telling the GPU that you don't want to draw a pixel here. At this point in time, you don't want to draw a pixel. Don't draw anything at all. I did all this math, and I figured out I don't want to draw a pixel. So this kind of fixes it, but then gives you other problems. Now you see now you can kind of see that there's circles again, but now you got these weird artifacts. You'll see that there's like white borders around our circles. If you go far away, you can kind of see them. So our alphas are now smoothly transitioning. The particles are still kind of just popping out before they fully fade out. I don't know why. But it's smoother, but you got that weird border effect going. So, like I said, I tried to do it. It just doesn't work very well. So I'm just going to go back and swap the blending modes for our rendering. So if I so everything's back to normal. So now this is really the gist of it. All right. So at this point, if all you care about is just learning this part, you can kind of leave the video and done, because I'm going to be talking about other. You can kind of leave, but if you want to stay, I'm actually going to start tweaking and changing this effect and doing a bunch of fun things with it. So if you want to stick around and just watch me mess around and actually change this effect into different things, stick around. Else, if you just cared about how this all works, you can leave now and save yourself 10, 15 minutes of time. Okay, so if you're sticking around to see me mess around and change the effect, let's play around. Let's play around with our shaders. So one of the first things I want to do is I have gravity applied to our velocity. So I'm going to get rid of it, go into compute shader, and I'm going to comment out gravity. Like, we don't need gravity. All right, so gravity, bye-bye. So if I go here, empty cache and rehard, now you'll see our particles now fly straight up in the air. And now it's kind of creating kind of like a smoke type of effect. That's what I'm kind of trying to get to. I wanted to make this look like smoke. So it's kind of like a smoke for Minecraft, like this low poly smoke effect going on. So get rid of gravity, and we want velocity to go straight up, and eventually it'll just fade away. Let's see, what else can we do? Are we done with this one? So I don't think I need to do any real other changes to computing. Yep, no more computing. So now we're just going to do changes to rendering. So the next thing we're going to do is we're going to scale it. So we're going to scale our vertices. We're going to make them smaller, bigger, or vice versa. So our age, our lifetime span is between 0 and 1. So I want to use that as a scale value. So instead of using from 0 to 1, I'm going to invert it. I'm going to make it to 1 to 0. So if life just started, instead of it being 0, I want it to be 1, and so I want to scale it at times 1. I want this. Basically at the beginning of its life, I don't want it to be scaled. The closer it gets to death, I want it to scale it down, and that's what I'm doing by inverting it and then multiplying it by position. I'm actually scaling the vertice down as it gets older. So if I save that, refresh, now it's starting to look like smoke, because that's what smoke kind of looks like. It kind of goes up and kind of dissipates. I think I'm saying that word wrong. Let me go to test, and gotta go all the way to the top. Oh my god. Here we are. Let's do 1,000 particles. Let's make it 10 times more particles than before. Empty cache. There we go. You get a lot more poofiness going around. So there's our smoke, and it gets smaller as it goes. So that's basically basically turning this into a smoke effect. But what if we just want to do something different? Let's say we want to scale it, but we want to scale it backwards. Instead of going from big to small, we go small to big. So we take the invert away, and we just scale it based on that. Boom, 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 boom. There you go. Now we went from smoke to basically, let's say if we're like the bottom of the ocean, and there's a hole in the ocean that's leaking out air, and this is basically now from smoke to like bubbles. This is like a bubble effect in underwater. So there's a pipe underwater, and there's a hole in it, and it's creating all these bubbly effects. So it's so like I said, we're by just changing a couple small values, we went from just a bunch of particles moving around to some kind of like a smoky effect, and now we again, by just changing 1 or 2 values, now we make it look like bubbles. And one more change I want to do just for fun, and we could do it in the Fragment Shader. We apply the age value, or basically the alpha value, to the red channel in our vertice. So instead of black, we're going to blend red instead of this. So if we empty share, that goes, and there we go. Now, if you want, you can say let's say this was like a part of a neck on a 3D character, and you cut the let's say you cut the like a maybe not a neck, maybe someone's stomach or something or something, and now you're spitting out blood, like you're just gushing blood out. So now like just by changing the color, now you can say, oh look, I'm just splashing out color. I guess with if you're dealing with blood, probably makes sense to add. Go back to feedback. Probably a good idea to add gravity back, because blood doesn't squirt out, kind of squirts out but then curves because of gravity. Is it working? Yeah, it's kind of coming down. So I think you guess this kind of it's falling, whatever, and you can kind of say this is low poly blood that's gushing out from your like. To me, this is how, like, if I were to say this is blood, I would say this is how blood looks like in Minecraft if it's gushing out of a character. It just gushes out like this, blip, 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 and it just falls back down onto the floor. If I were to compute this in a different way, I'd probably compute it to fall at a more wider curve, so it looks more realistic. But there's something you play around with numbers, with the velocity and direction that you want everything to move. So so it's kind of cool, like how with the small tweaks here and there, we were able to do a couple of different types of effects based on color and scale and velocity. We can simulate a couple of things here and there just by small changes by using the particle system that we just applied. In the next video, I want to be able to randomly create all our particles on the floor and have a texture in our quad, and a texture of like a blade of grass, and then instead of scaling it, I want to skew it on an animation. So this way it looks like the grass is flowing because of wind. So that'll be the next video I want to do, which I think will be fun because I need to bring textures back into this. We haven't done textures in a while. So, and ever since I refactored fungi, I can't bring in textures. So I need to fix up fungi and the loader to bring textures back in, and then start applying them to shaders. So the next video we're gonna do a field of grass, and we're going to abstract all the code away. All this code that all this code it will be abstracted away. So this way we can we still have to set up our buffers, but we're going to do it in a small, easier way. We're going to set up it kind of as a configuration, instead of so that we'll have functions that read in that configuration and then do all this work for us. So it'll create all the buffers and put them in the right places and share them in the right way, and all this can be automated in a less insane way, because this is insane. But this is how it's done, bare bones, with WebGL, without any abstraction. The only abstraction that we currently have is just how all the rendering is being done and all the shadering, because we're up to like episode 54, 55 on this series. If you're new to this series, that's what we kind of do. We kind of try to do everything in bare bones a little bit, and then we abstract it away, because we don't need to deal with it, because it becomes boilerplate. You should never really code like this. And then you prototype this way, but when you're done prototyping, you do something called like I forgot the term is. When you go back and kind of redo it, refactor. You refactor everything. Refactor it in a more smart and intelligent way. Almost time for me to go. So I got to cut this video probably a little short in a few minutes. But yeah, so yeah, just you don't code this way. You really want to prototype it, learn how it all works, and like I was up till 5 o'clock last night actually refactoring all this, and I literally sat there for like 2 or 3 hours staring at it and just writing out like fake code to get an idea of how do I want to implement this in a smarter way, so this way I can abstract it away, so it's where it's still flexible but still kind of easy for me to use it, and flexible enough where I can change things without actually have to go back in and adding too much to the functionality. So yeah, it took me 5 hours to refactor this into something that's easier. So yeah, good thing I didn't have to work today. So I was able to stay up really late last night, do all this coding, and then this afternoon write a video about this data. So I'm more kind of like halfway done, ready with the content for the next video. So that's it. That is our particle system that we've been developing. There's 3 videos in, and now we're starting to create some really cool effects. We can do a lot more things. By the next video, we can start be able to do a lot of things. Once we have all the abstraction, we can start doing blades of grass. We can do asteroid fields and things like that. We can do a lot of things like that. We just need the mesh data to do it. So if you guys have any effects that you really like to try out and really do, share them with me. If I think the effects are really neat, I might actually make those like priority of things to do instead of some of the effects I'm planning on making, for videos. And so yeah, all the effects we're going to do is going to be coded. It's like I might actually look at some Unity videos and how you use Unity to a particle system and how to make those effects. Then I got to look at it and say, okay, now I understand how those effects works in Unity. How do I code that? Because we have to build everything from scratch. We don't have a particle system that we just have to, use our mouse and pick the right settings and call it a day. We actually have to code these. We have to create the shaders. We have to make sure that our particle system can handle what we want it to do. So it's a lot more work, but in over time, we're going to build a particle system that maybe they'll be at least half as good as Unity particle system, where we can probably just put in, okay, here's a velocity, here's a lifespan, take care of the rest. Do all the work for me after that. So this way, the configuration part that I set up won't be something we need to do because it'll be automatic as well. So it'll be like a second layer of abstraction. So the first layer of abstraction I put together is to make it easier to handle creating buffers. And then in the future, we're going to have a second layer of abstraction that actually handles the configuration for you automatically based on what features you turn on and the values you put in. That's how Unity works. It's just features and values you put in, and it does everything. And the final emitter, I guess at the end when we have a pretty good particle system, would actually create shaders for you. Because that's what Unity does. It creates a shader dynamically based on the features and the data you feed into it. So right now we're creating all the shaders manually, but in the future the shaders should be generated dynamically for you if we have a pretty good particle system. All right. So there you go. Hope you enjoy it. This is really good stuff. Yeah, this kind of looks like low poly blood to me. This is kind of funny. It's like blood cells like flowing in those videos that you sometimes see in biology or Discovery Channel or whatever. So yeah, it's kind of neat. So yes, please like and subscribe. If you have any friends, please have them subscribe to me. I'm kind of hoping to. It won't happen, but I would love to try to win a plaque from YouTube. And I think you get like an award for only having the first award you get is like 100,000 subscribers. So I really don't necessarily care about views. I'm not looking to make tons of ad revenue money or anything. I actually really make no money off these videos, really. You'd be surprised. I probably made the total of like maybe $20 in this whole year. But like I said, I'm not doing this for money. I'm doing this because I love this. This is what I want to do with my life. In the future, I want to be a game engine developer or just an AR VR developer that can build these things from scratch. That's where I want to go, and this is what this series is going to follow. It's me going from a noob all the way to maybe someday working at Valve or working at Unreal or hopefully maybe EA or wherever. If I had a choice, I would probably want to work on a Fable game because I love Fable and I would love to make a game like Fable. I'll probably end up making my own Fable game before I ever work for a game company. I think ideally what I would love to do, in all honesty, I guess if I had a choice of what I can do, I want to make Sketchpunk Labs a really good indie game developer group. Right now, I just want to do it myself, learn as much as I can, build up an engine, build something from the ground up, and I will love to, and I'm the reason why I want subscribers and I want to get that plaque is I want a little bit of recognition for Sketchpunk Labs. Even if I never end up creating a game company myself, having make a little plaque on the wall that says, you know, that I made a choice. I went forward. I went a choice to try to live my dream, and in the process trying to help other people learn to live their dreams, because I'm not the only person who wants to be a game developer. I know I'm not the only person who wants to do these things from scratch and do this, because there's a lot of people that love it. It's just not enough information out there that really teaches you this from scratch. So, you know, in a way, I'm probably recruiting developers for my future gaming company. So, you know, if you're learning and you get really good at this, maybe in the future we can group up and make a really great game in a couple of years. So, but like I said, so I kind of want a lot of subscribers. I just want 100,000 subscribers. I want to get that plaque from YouTube, put it on my wall that says Sketchpunk Labs. I would consider that probably the first award of hopefully many in the future that Sketchpunk Labs will get. So if you want to just help me out, just help me get more subscribers if you can. That'd be awesome. That's the only thing I'd ask for, just more subscribers. I don't need Patreons. I don't need views. I don't need I don't need money. Like I said, this is for love, and I just want like a little physical thing that shows that my love can be attained, I guess, in a way. Like I said, I wanted it to be the first award of many. That I hope to have in the future with the name Sketchpunk Labs on it. Thanks again for joining the ride. I've been doing this for almost 11 months now. We're almost reaching the 1 year anniversary come January 4th or January 6th. This channel and this series has been almost a year old. I hope you guys have been learning a lot. Surprised it took me almost a year to get to this point. It's kind of sad, but anytime you hear about people building game engines from scratch, it really takes a while. It really takes a long time. Sometimes it takes the first year is just building the engine, and then the second and third year is when they can start actually building their game. So it's a long, long process. If I really wanted to be a game developer, I would just use Unity or any other game engine. But like I said, I want to do it my own way. Like I said, I don't want to be the guy who can use Unity. I want to be the guy that can build Unity and build games with my version of Unity. And I think a lot of people, especially whoever's watching with me, watching these videos, probably feel the same way. So good luck on your endeavors, and hopefully I'll see you guys in the future. Maybe I can hire you guys as some of my future game developers for Sketchpunk Labs. So again, like and subscribe, and please help find me new subscribers. That'd be awesome. So I guess I can see you guys in the future. And the next lesson, we're going to make some grass.